In this example, we're going to estimate the mass of the Earth's atmosphere. This example will include several key concepts such as defining systems, working with extensive and intensive properties, density, pressure, and temperature. The first step to solving a thermodynamic problem is defining the system. The schematic shows the Earth and its atmosphere not to scale. The system of interest is the gas that forms the atmosphere, and so the system boundary is drawn to include the gas, but not the Earth itself. Note that we don't need to know the exact thickness of the atmosphere to define the system. We can let the governing equations tell us as the analysis progresses. If the Earth were included in the system, we would also need to include it in the governing equations. For this analysis, we will assume that no mass enters or leaves the atmosphere, that no energy enters or leaves the atmosphere. In other words, we're treating the gas of interest as a closed system. The mass can be computed from the integral definition based on density, which says that the mass is equal to the volume integral of the density times the differential volume. Density is an intensive property that varies from point to point within the system. In order to solve the problem, we require a governing equation that describes density as a function of position. The ideal gas equation of state relates the thermodynamic properties of density, pressure, and temperature to each other. We'll discuss the ideal gas equation of state in detail as the course progresses. In this form, the Greek letter rho represents the density in kilograms per meter cubed. The P represents the absolute pressure measured in pascals, which is a Newton per meter squared. And the T represents the thermodynamic or absolute temperature measured in Kelvin. The M represents the molecular weight of the air in kilograms per mole. And finally, the R represents the universal gas constant, which has units of joules per mole Kelvin. Measurements of the atmosphere have led to many different models of the behavior of the air. For this example, we'll use simplified models that describe the variation of the temperature and pressure as a function of altitude. The temperature model is a linear relationship beginning at standard sea level temperature and decreasing as a function of altitude. The standard sea level temperature is 288.15 kelvins, and L is the temperature lapse rate, which is the rate the temperature decreases in altitude. It has units of kelvins per meter. The model of pressure versus altitude is slightly more complex. P0 is the standard sea level atmospheric pressure, which is 101.325 pascals. G stands for the Earth's standard acceleration due to gravity in meters per second squared. The temperature lapse rate, the standard sea level temperature T0, the molecular weight m, and the universal gas constant R appear again as defined above. Combining the pressure and temperature relationships into the ideal gas law results in density as a function of altitude, which is the governing equation for this problem. To estimate the mass of the Earth, this function of local density must be integrated over the volume of the atmosphere. To simplify the analysis, we can unwrap the Earth's atmosphere and treat it as a cube. Note this is not strictly valid, and a more accurate result would require use of cylindrical coordinates. However, for the sake of approximation, the use of rectangular coordinates achieves a good estimate. Unwrapping the atmosphere, we can represent its volume as a box, with coordinates x, y, and z. The differential volume, dV, becomes dx, dy, dz. And our volume integral becomes a triple integral. Integral from x1 to x2, y1 to y2, z1 to z2, density as a function of x, y, and z, times the differential volume dz, dy, dx. Note our density equation is only a function of z. We can perform the x and y direction integrals directly, as for any constant. Note that the x and y terms multiply to give the surface area of the Earth. Our final equation to be integrated becomes mass is the area of the Earth times the integral from sea level to the height of the atmosphere times our density function. Although we may be able to perform this integration analytically, I'm going to use a mathematical software package to save time. First, I define my constants and my functions. The plot of temperature versus altitude shows that the value for temperature crosses zero around 20,000 meters. Negative absolute temperatures are not defined, which tells us that this model is not valid above this altitude. This altitude may fix the upper limit of our integration, depending on whether or not the pressure function shows a more severe limitation. The plot of pressure shows that the pressure model does not limit our analysis further. We will use 19,000 meters as our limiting altitude for this integration. In reality, 75% of the mass of the atmosphere is within 11,000 meters, though the atmosphere actually extends well beyond 120,000 meters. Finally, we can compute the integral and arrive at a value for the mass of the atmosphere of about 5 times 10 to the 18 kilograms. To improve our understanding of this result, let's compute how thick the atmosphere would be if it were made of water. Dividing the mass of the atmosphere by the area of the Earth gives the mass of the atmosphere above each unit area of Earth in kilograms per meter squared. Dividing this result by the density of water, 1,000 kilograms per meter cubed, results in the height of the atmosphere if it were made of water, 9.78 meters, which when we convert to feet is about 32 feet. The result of 32 feet is a confirmation that we arrived at a good estimate. In scuba diving, a rule that divers follow is that each 33 feet of depth adds the pressure of 1 atmosphere. This follows from the hydrostatic concept that we discussed in class, that pressure equals density times the acceleration due to gravity times the depth of the water. Computing the pressure for 32 feet of water, or 9.78 meters, the density, 1,000 kilograms per meter cubed, the acceleration due to gravity, 9.81 meters per second squared, times the depth of our water, which is 9.78 meters. This results in 95,941 pascals. The standard atmosphere is 101,325 PA. Let's compute the error percentage. Subtracting the true value from our computed value and dividing by the true value and multiplying by 100% results in an answer of minus 5%. And so our model underestimated the height of a water atmosphere by about 5%. Which isn't very bad considering the many assumptions that went into our model. To summarize, first we defined our system, including everything that is in the system, the boundaries of the system, and the interactions that occur at those boundaries. Next, we developed our governing equation using the definition of density and the ideal gas law. We then set up our integral of density over the volume of the atmosphere by defining a coordinate system and a differential volume element. We simplified the integral by recognizing that the density only varies in the z direction. This caused the surface area of the Earth to fall out of the triple integral, leaving us with an integral in the z direction. Next, we used a mathematical software package to inspect the temperature and pressure functions and determine the upper altitude limit of the integral based on the value of the temperature function. We then computed the integral and arrived at a value. Finally, we compared the value to a recognizable example by computing the thickness of the atmosphere if it were composed of water instead of air. We found that the thickness of the water atmosphere agreed well with our understanding of hydrostatic pressure. That concludes the example. Thanks for tuning in and have a great day.